Hi viewers, welcome to the follow-up video on orthotropic materials. So if you haven't seen the first video, I would request you to see the first video on orthotropic material. It will be right there below in the description. Now, just putting things into perspective, in the first video we looked at the relevance of orthotropic materials. A composite filament wound pressure vessel is a very good example. So the winding angle can be so chosen that it will be twice as strong in the hoop direction compared to its axial direction. So an example is a composite filament wound pressure vessel. The fiber can be made of anything, okay? The winding angle should be such that that constraint is met. Then I went on to describe you a few examples of orthotropic materials: wood, a unidirectional laminate, honeycomb, and a few of the human bones are modeled as orthotropic materials in recent studies in prosthetics. Then we kind of introduced or we kind of started talking about engineering constants. If you remember, for an isotropic material, we just require two constants, Young's modulus and the Poisson's ratio, to completely describe the response of that particular material against a given loading. When it comes to orthotropic materials, since its properties are different in different directions, it is quite intuitive to believe that there will be a few more constants other than the two. So that intuition is quite valid. We have more number of engineering constants for an orthotropic material. So now let's go ahead and have a look at them in more detail. Before we start talking about the engineering constants, let me briefly talk about the general stress state in a three-dimensional object. This won't be a very elaborate discussion on the general stress state and all, but this here we will keep things pretty brief. So general stress state in 3D can be denoted like this, can be denoted as shown here. So we have a point in a 3D object, and then we are assuming this small cube around that particular point, and the stress state at that particular point can be described with the help of this particular thing called the stress tensor, or better to call it a stress tensor. If you are totally new to the tensor algebra and all those things, don't worry, for the time being just take it. That essentially means it's a matrix of 9 elements, and it's a symmetric matrix, and it comes from the fact of balance laws. Again, I won't get into that. Most of the practical applications, the stress tensor will be a symmetric tensor, second order symmetric tensor. So you need 6 quantities: the sigma 1, tau 1 2, tau 1 3, sigma 2, sigma tau 2 3, and sigma 3, to completely define the stress state. Because once you know this particular half, then this half is already known, because tau 21 is equal to tau 1 2, tau 31 is equal to tau 1 3, and tau 32 is equal to tau 2 3. Sigma 1, sigma 2, sigma 3 are extension normal stresses, so they give you an indication of the stress acting perpendicular to a given phase, as shown here. Sigma 1 acts perpendicular to the phase 1, sigma 2 acts perpendicular to the phase 2, and sigma 3 acts perpendicular to the phase 3. And while tau 1 2, tau 1 3, and tau 2 3, and tau 3 2, they are shear stresses. Shear stresses, they act along the plane, they cause shear deformation as shown here. So this is basically the 6 components in the stress tensor. Now similarly, we will have a strain tensor as well, and we will have 6 strain components. I won't get into the details of it. Now we have 6 stress components and 6 strain components. If we know the strain components, you can predict the deformation. and from the forces you can calculate stresses. Now you need to connect these two. You need to connect the stresses to the strains, and for that we need engineering constants. So let's go ahead and look at it. For the easiness of explanation, let's may take some notations as defined here. These notations are very widely used in most of the textbooks. So sigma 1, sigma 2, sigma 3, they are the respective normal stresses, and epsilon 1, epsilon 2, epsilon 3, they are the respective extensional strains or the normal strains. While sigma 4 is a variable to denote tau 32, which is the shear stress in the plane 32, and sigma 5 is used to denote the shear stress in the plane 1 3, and sigma 6 is used to denote the shear stress in the plane 1 2. The best way to remember is that if you sum up all the indices like 4 plus 3 plus 2, you end up with 9. Here as well, if you add all the integers like 5 plus 3 plus 1, again 9, and here as well 6 plus 1 plus 2, you again end up with 9. So that's quite a trick usually people from applied mechanics use to remember these notations. So you have 6 parameters here, and you 6 stress parameters, and here you have 6 strain parameters. These are the shear strains. Okay, now to connect, this can be thought of as a 6 by 1 matrix, and this can be also thought of as a 6 by 1 matrix. Now you need a 6 by 6 matrix to connect these two. For an orthotropic material, this is the way how the strain vector is related to the stress vector, like this. See, here you have just 9 constants. I'm not going to explain you how this matrix assumed this shape like this, because it is beyond the scope of this particular video. If you guys demand me to do a video on that, then I can do that, but for the time being, let's keep that aside, because I'm here to tell you the relevance of these constants or the meaning of these constants. So for an orthotropic materials, this is how the matrix looks like, and this is called the compliance matrix, because you have strain on the left hand side and stress on the right hand side. That's why it is called the compliance matrix. This can be pretty much remembered like this, because when you have deflection is equal to the applied load divided by the stiffness, where 1 by stiffness is your compliance. So a pretty easy way to remember that. This will be analogous to a spring. Okay, now let's go ahead and assume a situation where you are only applying sigma 1. Okay, nothing, no other force, just sigma 1 alone. Then what will be the expression then? So that is my case 1. Let me put it down here. So in case 1, I have sigma 1 not equal to 0. All other sigma i's will be 0. Then my epsilon 1 will be S11 sigma 1. So you know, for this to satisfy, my S11 should be 1 divided by E1, where E1 is the Young's modulus. So applying Hooke's law, because this is everything is in the linear regime, nothing has gone to the non-linear regime. So the Hooke's law is pretty much applicable. This is a linear material. Okay, the difference between linear and isotropic is well to be understood. Okay, we are talking about a linear orthotropic material. So going by the similar argument, your S22 will be 1 by E2. Similar argument in the sense, in the next thought experiment, you assume your sigma 2 is not equal to 0 and all other stress components are 0. Then S22 will be 1 by E2. Now S33 is 1 by E3, where these E2 is the Young's modulus in the direction 2 and E3 is the Young's modulus in the direction 3. So, having seen what the relevance of what is S11, S22 and S33, they are related to the Young's modulus in their respective directions. Now let's go ahead and see what is the meaning of or how we can physically appreciate this constant S44, S55 and S66. In this case, let's assume you apply sigma 4 along, then your epsilon 4 will be related to S44 like this. The key takeaway is that your epsilon 4 is your gamma 32, then your S44 and sigma 4 will be your tau 32. So S44 is the inverse of your shear modulus in the plane 32. Using a similar argument, your S55 will be inverse of the shear modulus in the plane 1 3, and similarly your S66 will be the reciprocal of your shear modulus in the 1 2 plane. So this explains the relevance of the 6 constants, or how they are related to the parameters which we know physically or which we know already. So we started off with a matrix like this. We know the physical relevance of S11, S22, S33, S44, S55, S66. Now for an orthotropic material, we are left with these 3 now. How we can relate them to some of the engineering constants that we can physically appreciate? Let's go ahead and have a look at it. For explaining that, let's define a new set of Poisson's ratios which is generally defined like mu ij, where mu ij is defined as minus epsilon j divided by epsilon I when you have only stresses in the I direction. This is pretty much similar to the conventional Poisson's ratio, but defined in a much more general case. For example, mu12 will be defined as minus epsilon 2 divided by epsilon 1 when sigma 1 is applied. Okay, so keeping this in mind, let's go ahead and think of another thought experiment. Let's say sigma 2 alone is applied, then extensional strain or the normal strain in the one direction can be written like this, pretty obvious from the above matrix. Since other 2 stress components are 0, you end up with an expression like this. Then using the definition for epsilon 21, it's a bit clumsy over here, but no issue. So mu21 can be defined like this. Now plugging this, because this equation is valid because I am applying only sigma 2. Substituting this equation back here, I will end up with this. Now doing a little bit of cranking the mathematical wheel, I am here just rearranging the equations. Now what is epsilon 2 divided by sigma 2 when sigma 2 alone is applied? That is nothing but the reciprocal of Young's modulus in the second direction. Makes sense? So S12 is related to the Poisson's ratio in the 1 2 plane as well as the Young's modulus in the second direction. Using a similar argument, your S13 can be defined as minus mu31 divided by E3, and the last one, your S32. By last I mean this, like you have that long expression, the matrix over here. So now I know S12, I know S13, now I left with S23 alone. So using a similar argument, S23 can be written like this. S23 can be written like minus mu 32 divided by E3. Makes sense? So with this we have successfully shown how we can physically appreciate the 9 constants that are required to completely describe a particular orthotropic material. Thanks for watching.